So I'm just going to go over, there's a couple of problems that we kind of skipped around and didn't do when we were going through this or finishing going through this on Monday. So I'm just going to go back to those few problems. And then, so from 8.5, excuse me, to be more specific. And then I was going to open it up to questions that you might have. Okay. So the question we're going to start with is a Montana millionaire question. So originally when I wrote this question, this is the true data from this year's Montana Millionaire. And if you're not familiar with Montana Millionaire, it's not even a lottery because it's really a raffle. They sell 250,000 tickets, each $20 a piece, and there's guaranteed winners. So there will be $2 million prizes this year. One second place prize of 25,000, one third place prize of 15,000. Then there was 1,500 instant win prizes of 500 and 1,000 instant win prizes of $100. And I originally wanted to compare this to what they did last year because they only offered one $1 million prize, but I couldn't figure out if they had sold 250,000 tickets last year or 125,000 tickets. So I couldn't compare based upon what the information they have on the lottery website. I couldn't compare it between the two. But we'll just focus on this year. The only reason why I was saying that is that I wanted to see if the expected value changed in terms of what you would expect your return to be. And if this year, with there being $2 million prizes, were your chances on your expected value return better than last year, that type of thing. So, but we can't. So we're just going to focus on this. So when we're looking at lotteries or playing games, anything that we're paying money into, when we look at the return, we always have to subtract off what the money we're getting back. So we're going to say let X equal the money won. Okay. So if we write our probability distribution or table, so we have X and the probability that X equals X, we're going to have 1, 2, 3, 4, 5, 6 different outcomes. It's a big table. So again, we're assuming that we're just buying one ticket. We're not going to get into like, well, about 10 tickets or anything like that. It's just, what if I buy one ticket? What is my return for this? So if there is a $2 million prizes and I pay $20, does that mean I get $1 million back? Well, no, you actually get $999,980 back because we have to take our $20 investment off of that. So the probability for that first outcome is going to be 2 out of those 250,000 tickets that are sold. For the second place, and really the second and third place drawings, they're not even second and third place, they're considered early bird drawings. They draw them before they do the final drawing. But for ease of us discussing this, we'll say it's second and third. So the next prize is 25,000. So again, with each of these, we have to take the $20 investment off. So we're really going to have 24,980. And there is one out of those 250,000 tickets that will get us this. For the 15,000 prize, again, taking that off, we're going to have 14,980. And again, there's one out of 250,000. Then we've got those instant winners. So you can get an instant win of 500, which really means you're only making $480. And there's 1,500 of those out of 250,000. Then we've got 1,000 instant wins of 100, which really means we're only getting $80 back. And so we always focus on the money we can win, right? Well, we forget about what happens if we don't win anything. that means we are out $20. So it's a negative 20 for our return. And in order to find this, we're going to add up the probability part. So we have 2 plus 1 plus 1 is 1,500 plus 1,000, which gives us 2,504 tickets. So if we take that off of 250,000, we get 247,496 tickets, which means the probability of losing our money is real high. It's 247,496 out of 250,000. And again, even though it's more likely that we will lose, if we're thinking about playing the lottery or somehow getting free money, this is our best probability in general of earning $1 million from a lottery situation, because the actual lottery is a crazy small probability versus this, we're doing better, right? There is a possibility that we could win. So I want you to find the expected value. This is one where using your calculator to enter list 1 and list 2 is going to be really helpful, because these are big numbers, and instead of trying to write this all out, that's going to be a pain in the butt. So go ahead and use your calculator to calculate the expected value, and send me your answer to the nearest penny. All right, so our expected return is negative $8.44. Woo, big winning, right? So again, you're not likely to win, right? If we think about, but it's possible, because it's not like our expected return is just negative $20, which would be, you'd have no probability of winning. There's a slight probability of winning, but it's still in the favor of Montana Millionaire and not in our favor. So I'm going to insert another problem that's like this. I'm going to have you do on your own. And so let me write out the problem. So expected payback and expected value are the same thing. So there's a raffle. It offers one first place prize of $1,000, two second place prizes of $300 each, 20 third place prizes of $10 each. And then overall, they're selling 10,000 tickets that are sold at 50 cents each. And I want you to find, so it says, what is the expected payback? It's the same as the expected value. So again, the only time we subtract off our investment from the money returned is if it tells us that we've invested a certain amount. So what I'm saying is, because it tells us that we bought a ticket for 50 cents each, we need to take that 50 cents off what it is we're getting back. So again, first place, we're gonna have $999.50 because we're taking that 50 cents off. Second place, we're going to have $299.50. Third place, we're going to have $9.50. And then we can't forget that we lose 50 cents is our other option. So the probability for that is, for the first outcome is going to be 1 out of 10,000. Probability for the second outcome is going to be 2 out of 10,000. Probability for the third outcome is 20 out of 10,000. And again, to get the last probability, we're going to add up the tickets that are winners. So 1 + 2 is 3, plus 20 is 23. Taking that off of the 10,000, we have 9,977 losing tickets, basically. And so then our expected value here ends up being negative 32 cents. Again, it's a losing game. And remember, if it asks if it's a fair game, the answer is no, because the expected value for a fair game is 0. All right, which other ones did we skip? Okay, let's look at this one. So 3 balls are selected at random without replacement from an urn containing 4 black balls and 5 white. Let the random variable x denote the number of black balls being drawn. So we're selecting 3, right? And when we think about what do we have, so how many balls do we have total? Well, total is going to be 7. Nope, not 7, 9, excuse me. Right? Because 4 + 5 = 9. So of the 9, 4 are black and 5 are white. So what are our possible outcomes when choosing 3? We can have 0 black, 1 black, 2 black, and we can have 3 black because of the fact that there are 4 black total, right? So if we create our probabilities, so it can be helpful to just find the individual probabilities first before you try to create your distribution. So these are going to be combinations. And I'll give you a hint, the bottom is going to be the combination of 9 balls chosen 3 at a time. And I'll let you figure out the numerators. So go and find these 4 individual probabilities as decimal numbers to 3 decimal places and send me your answers. All right, so we've got, when we're looking at these, we always have to think, all right, our first two numbers have to add to be the first number in the denominator. Our second two numbers have to add to be the second number in the denominator. So we end up with 0.119 if we're just going to 3 decimal places, 0.476, 0.357, and 0.048. Again, it's asking us, I'm not bothering to list the outcomes of the experiment. We're finding, we just are finding the probability in order to do the distribution. And so if we were to do the probability distribution, we're gonna have 0, 1, 2, 3, and so again, we're just finding our individual probabilities for each of those, and then we're gonna write it in table form. If we go back up to the questions that it had, it says list the outcomes of the experiment. If we were to draw a tree diagram for this, we could think that we've got black or white. And then again, this is going to look kind of like what we've done with our previous tree diagrams. Because we're only choosing 3 balls. And so the choosing of the 3 balls means that we're going to have 3 branches on our tree diagram. And so this is going to lead us to our outcomes of what the sample space is going to look like. Now, I'm not putting my individual probabilities through here as we're doing them. We're just looking at what is the outcomes. What does our sample space look like? And this is going back to what we were doing at the beginning of the unit. And some of this is even just what we did in chapter 7. So if we list the outcomes, we're looking at the set, and then we would just go through. So we can have 3 black balls. We can have 2 black and a white. We can have a black, a white, and a black. But because we are not allowing for replacement, we can't break this down like we did in the example for binomial probabilities. We're looking at the number of girls that we're having. Because we don't have replacement, the later probabilities depend on the initial probability with us selecting the ball and not putting it back in. So again, that's why we had to go to drawing the calculating the probabilities like we did here, because selecting balls without replacement are not independent outcomes. Part B says find the event consisting of outcomes in which the value of 2 has been assigned to X. So again, we're saying X is the number of black balls. And so if we go through and look at here, where do I have 2 B's? Those are all the places that 2 B's occurred. So we're going to say that that's black, black, white, black, white, black, and white, black, black. I'm not going to bother with drawing the histogram. And I think that's all of our examples from this. Oh no, we have one more. So it says 3 cards are drawn from a deck. Let X be the number of hearts in the hand. I don't like having you draw these. Drawing histograms is not necessary. We're just going to find the probability distribution. And then we want to find the probability that X is going to be greater than 1. So again, if we think about 3 cards are being drawn, X is going to be the number of hearts. Well, what can we have? How many hearts are possible? Well, we have 13 total cards. So if we're choosing 3 cards, it's possible to have up to 3 hearts, right? We can have 0 hearts. We can have 1 heart. We can have 2 hearts, or we can have 3 hearts. Now, obviously, we can't do all of our calculations for those individual probabilities within our table. So we were going to calculate them below. So if we think about our deck of cards, we've got a combination of 52 cards chosen 3 at a time in the denominator. If we think about our 52, it's broken down into 13 hearts and 39 others, basically, right? There's 13 other hearts, 39 that aren't. So I want you to go ahead and calculate the probability of 0, the probability of 1, the probability of 2, and the probability of 3. Send me your answers to 4 decimal places. Okay, so for probability of 0, we've got the combination of 13, choose 0, times the combination of 39, choose all 3 for our numerator, which gives us 0.4135. For the probability of 1, we have the combination of 13, choose 1, times the combination of 39, choose 2, all over the combination of 52, choose 3, which is going to give us 0.4359. Probability of 2 is the combination of 13, choose 2, times the combination of 39, choose 1, over the combination of 52, choose 3, which is going to be 0.1377. And the combination of 13, choose 3, times the combination of 39, choose 0, over the combination of 52, choose 3, gives us 0.0129. So when the instructions say to create the probability distribution, you need to have this table. You need all of that notation. You need to have that the X is the first part, the probability that X equals X. And remember that saying, what is the probability that our outcome is equal to that specific value? And so then you'll need to put your probabilities in here, because again, for your exam, it's going to ask you to write these out. And I want to make sure that you have all the necessary pieces. So it's not telling you to find the expected value. What it is telling you to do is define the probability that X is greater than 1. So the probability that X is greater than 1 means it's 1, 2, or 3. So there's two ways we could do this. We could add up the probability of 1 plus the probability of 2 plus the probability of 3. Or, and again, the reason we're limited to the probability of 3 is because it's still going on. We're just choosing 3 cards. So within those 3, what's the probability that it's greater than or equal to 1 means we have to max out at 3. So it could be 1, 2, or 3. We can also look at the complement event here, which is 1 minus the probability of 0. Okay. So again, we're looking at two sides of this. We have the probability of 0, which is the stuff that's less than 1. We can take that off of our probability of 1, or you can add up the individual probabilities. Either way, we are still going to get to the same answer. I personally do the 1 minus 0.4135 because it's fewer steps, not anything other than that. And we end up with 0.5865. So questions about that one? The nice thing about chapter or 8.5, section 8.5 is it really brings everything we've done in chapter 8 together, right? Because we have finding those individual probabilities, we have writing the probability distribution, and then you have the expected value and finding specific probabilities based upon the requirements. So that's why I like going with chapter or going over 8.5 a lot, because it still touches on all the stuff that we've already done in the rest of the chapter. So that's the last of the material I have for 8.5. And again, we've already gone over most of this. This is just more practice problems, but is there anything else you want to talk about that came up elsewhere? Okay. That's fine. No worries. So why don't we have this? Why don't you, I'm going to put a note in Online. I want you to email me if you want to have class on Friday. So if you come up with questions between now and Friday, email me. So today and tomorrow, email me if you want to go over them, and then we can meet. And if you don't email me, I'm going to assume that you don't want to have class. Okay. So just think about that and let me know. And I hope you all have a good rest of your day. Okay. Bye.